All right, let's jump right in. We're going to tackle a really fundamental question in chemistry and engineering today. When a chemical reaction happens, where does all that energy actually come from? We're going to explore how we keep track of the heat that's either spit out or sucked in when molecules get rearranged.
You've definitely felt this before, right? You mix a couple of things together and suddenly the beaker gets really hot. Or maybe it gets surprisingly cold to the touch. So what is actually going on at the molecular level to make that happen? By the time we're done here, you'll know exactly why.
Okay, let's get into it. To really get a handle on the energy of reactions, we have to start with pretty much the single most important rule in the entire universe when it comes to energy.
And this is it, the big one, the first law of thermodynamics. Honestly, the easiest way to think about it is like a bank account. You can't just create money out of thin air, and it doesn't just, disappear. It just moves from one account to another. Well, energy works exactly the same way. It's all about accounting.
So for any system, doesn't matter if it's a giant power plant or just your morning cup of coffee, the energy you put in minus the energy you take out has to equal the change in energy that's stored inside. These equations here, they're the fundamental tools we use to balance those energy books. This is our ground zero.
Now, that simple balancing act works perfectly, until the chemicals themselves start to change. A chemical reaction throws a massive new energy source into the mix that we absolutely have to account for. Let's dig into that.
This is such a classic example. We take hydrogen gas, we take oxygen gas, and poof, they react to form water. But this isn't just a simple mixing. It's a total transformation. Old molecules are being torn apart, and brand new ones are being built. And believe me, that process has some major energy consequences.
And this right here is the absolute key. You have to spend some energy to break the bonds holding the hydrogen and oxygen molecules together. But then you get a big payoff. Energy is released when the new, much more stable bonds in the water molecules snap together. The magic is all in the difference between those two numbers.
And what a difference it is. For every single mole of water you create, a net total of 250 kilojoules of energy is unleashed. Now, to put that into perspective, if you didn't have a way to pull that heat out, the source material says the temperature inside could shoot up by several thousand degrees. This is not some tiny, subtle change. It's a massive energy event.
So, because this energy is so incredibly important, engineers and chemists needed a specific term to define it, and of course, to measure it precisely. And that term is the heat of reaction.
Now, I know that definition sounds super technical, and it is, but for a very good reason. It's the change in a system's total heat content. We call that enthalpy. If you start with your ingredients at, say, 25 degrees Celsius and 1 atmosphere, and you end with your final products at the exact same conditions. Doing it this way isolates the energy from the chemical transformation itself and nothing else. This whole concept basically splits every chemical reaction into one of two camps. If the heat of reaction, that delta HR symbol, is negative, it's exothermic. It releases heat. That was our water example. It gets hot. But if that number is positive, it's endothermic. It actually has to pull heat in from its surroundings, which makes everything feel cold. So there you have it. That one slide pretty much answers the hot versus cold question we started with.
Okay, so now we know what the heat of reaction is. But we have to be careful. There are a couple of really important rules. Think of it as the fine print that you have to follow to get the right value. First up, and this one's a biggie, the quantities matter a lot. The amount of energy you get out is directly tied to how much stuff you're reacting. It's all about what chemists call stoichiometry. And this illustrates that rule perfectly. If you write the equation for burning 1 mole of methane, you get negative 890.3 kilojoules. Simple enough. But if you write the equation to show burning 2 moles of methane, well, the heat of reaction is exactly double that, negative 1780.6. The final number is completely tied to the quantities in the specific equation you decide to use. All right, rule number 2 is just as critical. The physical state of your chemicals, whether they're a solid, a liquid, or a gas, can totally change the final number. Just look at this. It's the same reaction, burning methane. But if the water you make ends up as a liquid, you get about 890 kilojoules of energy out. If it ends up as a gas, as water vapor, you only get about 802 kilojoules. So why the difference? Well, it's because some of that potential energy had to be used up just to turn the liquid water into steam. The state of matter is absolutely critical.
So we've got our basic energy balance from the beginning, and now we have this new special term, the heat of reaction. How do we actually put them together to solve real problems? It's time to zoom out and look at the final procedure.
Engineers use a really systematic procedure
kind of like this checklist to make sure they get the right answer every single time. They track all the mass coming in and out. Then they write that base energy balance we saw. They make a big table to keep all the inputs and outputs organized, and then they calculate the energy values for each one. All of this just leads them to the total energy change, correctly folding in our new heat of reaction term.
The whole point of that checklist is to be methodical, right? It makes sure no energy source gets forgotten, and it leads us directly to one final, all-encompassing equation that tells the entire story.
And here it is. This is what it all builds to. The total energy change for the entire system is really the sum of just two big parts. First, you've got the energy that's generated or consumed by the chemical reaction itself. That's our heat of reaction. Then, you add in the energy changes that come from just the normal heating, cooling, or pressure changes of all the stuff flowing in and out. This one equation ties everything together, and it lets us balance the energy books for good.
So if there's one thing to take away, it's this. By understanding and being able to precisely calculate the heat of reaction, we gain the power to control and harness chemical energy. It's the absolute foundation for designing safer chemical plants, building more powerful batteries, and even creating the rocket fuel that gets us to space. It all comes back to balancing those energy books.